it hasn't got because it has a fully filled D subshell, right? Imagine this now. Imagine this is the, I'm going to draw it here. You see here, you see the difference between this one, between copper 2 plus's split orbital and zinc's split orbital. There's no space in this higher energy orbital for electrons to get excited to. Likewise, there's no actually a space for it to get de-excited to, because all of these they're all full up, all full, all full, all full, all full. There's no space for any electron here, right, to get excited to here, because this is full and that's full. But more importantly, the first step is that this one is full. So if any electron here wants to get excited, there's no place for it to get excited to. Therefore, there'll be when light hits this, it may have energy to breach the energy gap, but there's no space for it to get excited to. So there'll be no movement of electrons here. And that's why zinc wouldn't have that property. Now, it's generally just a 1 mark question, so I'm not expecting it to be like a big thing in there. But just in case you're like thinking, oh, why does that happen? It's because there's literally no space for it to actually occur, right? Now, I mentioned in the past here that the light has to have a specific frequency. The wavelength of light has to have a specific frequency in order to breach the energy gap. Now, it's a bit of a physicsy thing that you need to understand. It's a bit of a physicsy equation that links to it, because this is, as I said in the start of this video, you need to understand both the chemical process. The chemical process, or the chemical understanding of this topic, is the movement of the electrons and the electronic configuration. But the physical aspect of it is we're talking about here the frequency of a specific wavelength of light. And you can actually calculate the energy gap from the wavelength of absorbed light by using the following formula. So we can link the energy gap to the wavelength of absorbed light as well as its frequency in order to actually help us work out the energy gap. So let's say we wanted to work out what an energy gap is. This could be very useful for people that want to work out if you just wanted to work out what the energy gap is, right? There's a way of doing it, and if you're able to get the frequency of light, we can link the frequency of light to the energy gap using this equation. And the equation is delta E is equal to HV, or you can use the equation delta E is equal to HC over lambda. Either one of those equations. Now you can probably see why, if you could think about it right now, you can probably think of why they're using either or equation, because there may be an example in the exam where you don't know. By the way, I don't think I think they give this to you in the exam, but if you don't, I'm not entirely certain whether or not they give this to you in the exam or not. Always check the specification. But obviously you have both equations here, so assume AQA to not give you the tell you which formula to use. You need to be able to work it out based off of the information that they give you. If they don't give you if they don't give you the frequency, but they want you to work out delta E, then assume that they're using this equation. Or they may not give you enough. They may not give you C, whatever, but you need to be, so it may be this one. Or they may not give you directly what the frequency is, but they give you enough information to work out the frequency. They may not give you what, again, and you can see where this is going. They're never going to specifically always just give you the information. They'll give you information to work out the information that you need to use to substitute into your equation. But you guys are smart about this now. You know how AQA works. You know how they try to twist things. Just be aware of these things in your exam, because you may look and say, how I'm meant to answer that question. It's like, no, you have all the information there to answer your question. You just need to be very, very careful about how you approach it. So what is HV? What's HC over lambda? I probably should have went through that part first, right? So delta E is the energy gap so this is just the energy gap in kilojoules or joules per mole, right? H is something we call Planck's constant, right? Now, this is more of a physicsy constant, so you don't have to, and you give this to you in your exam, so you have to memorize this, but I have it with me here. It's actually equal to 6.63 times 10 to the power of minus... Did I save it on me right here? Hopefully I did. Yes. 6.63 times 10 to the power of minus 34 joules second. Not joules per second, joules second. Right? And we have the joules we have in that equation as well, right? So that's Planck's constant. V represents the frequency of light in hertz, right? So V is the frequency of light in hertz. So if you want to work out delta E and they give you the frequency directly, or you've been able to work out the frequency, then you can just use HV, and I will give you the energy gap, right? So that's your frequency. That's a terrible Y. Frequency in hertz. Or you can use a separate equation, which is hc over lambda. So h, again, is just Planck's constant. C is the speed of light. Now, you don't need to know the physics constant for speed of light, because I think in AQA physics, they use the one that's more accurate, which is actually 2.97 times 10 to the power of 10 to the power of 8 meters per second. But you just need to know, all you need to know is the AQA chemistry standard for speed of light, which is rounded to 3.00. Actually, you don't need to know it. They gave it to you in your exam. They gave it to you in your exam. I thought you had to memorize it. You don't. You really don't. It'll be given to you in your exam as 3 times 10 to the power of 8 meters per second. They give that to you in exam. And lambda is just your wavelength. And it's in meters. It's not in picometers or nanometers or anything like that. Wavelength is in meters because we keep the SI unit. It's an SI unit. So, because wavelength is just a distance, and distance is always measured in meters. Right. Now, I want to make it very clear that, as I said before, as I said in the start, the very first thing I said about colors of ions is that it's a feature or it's a property of transition metal ions that transition metal ions give specific colored ions, right? And as I said, I explained to you what's going on chemically and physically, what's going on in terms of that energy gap, right? So the energy gap really is what determines the color of the ion, or what wavelengths of light are getting absorbed, what's getting emitted, what's getting reflected back. But it's important that, so as I said, the energy gap is what determines the color that you see. But the energy gap is dependent on the metal ion that you have, its oxidation state, the ligands, and the coordination number, right? So it's metal ion. The metal ion, no, I just put like a little, that's already highlighted anyway. Yeah, the metal ion, the oxidation state, ligands, and the coordination number all determine, all have an effect on the coordination number. And that's obvious, right? So if you have a metal ion, if you have two different metal ions, then of course they're more likely to be a different color. But if you can have the same metal ion but with different oxidation state, for example, Fe2 is a pale green, but Fe3 is like kind of like a pinkish type of color, or more of a violet type of color. Sorry, I've got to be specific there. Fe3 plus is actually, Fe3 is violet, whereas Fe2 is a more of a pale green. Ligands, you may have the same transition metal ion, but it has different ligands. So iron 2 hexa aqua may be of a, or it will probably be of a different color to that of iron to hexaamine. The ligands will also affect that energy gap, and also the coordination number. If you have a tetrachloride instead of a obviously tetrachloride, if you have a penta-aqua instead of a hexa-aqua, that could, the coordination number in that sense would affect the coordination, the energy gap. So all of these things here, and you will need to understand that you need to know that the metal ion, the oxidation state, the ligands, and the coordination number all affect the energy gap, and different energy gaps correspond to different colors that you would see. Now, the colors for transition metal ions. So, the colors for transition metal ions depends on the color of the light that is absorbed. So, the absorption process. So, when a transition metal ion is in light, it'll absorb the frequencies which correspond to the d subshell energy gap. The rest of the frequencies will be reflected. So, you only see the reflected light. So, as I said, as before, the rest of the frequencies of light will be the transition metal ion will when transition metal ion is in light, it's absorbing specific frequencies of a particular wavelength of light that correspond to that d subshell energy gap, right? But all the other wavelengths of light that don't correspond to that d subshell energy gap will just be reflected back, right? You only see a reflected light. Of course, there's the emitted light as well, and we also see all of these lights together, the reflected light and the emitted light. We all see that as the complementary color. That's the color that you see. The reflected light, the emitted light, they all correspond to the complementary color, and the complementary color is the light that gets emitted or reflected back to you. That's what you see. So absorption examples, right? So suppose you have a metal complex which absorbs red light. The red light is removed from the light that you can see, and you see the rest of the colors in the spectrum. So the complex appears blue. Right, I mean that just makes sense. If something absorbs anything in the red end of the spectrum, now knowing red, it actually has quite a lower frequency, so it actually probably has a lower, for example, copper 2 hexa aqua. You don't need to know this, by the way. I'm just saying because I just know it. The red end of the spectrum is generally of a lower wavelength from lower frequency, so it probably has a much lower energy gap. That's what I would assume. So it's absorbing all the red light, so you don't see any red because it's absorbed all the red wavelengths of light, and it's reflecting back the blue wavelengths of light. That's why it appears, that transition metal would appear blue, because it absorbed all the red light. So there's no red light for you to be able to see, because it can't be reflected. It's all being absorbed, but it's reflecting back all of the blue light, right? So metal ions that absorb red light do not appear red because there's no red light for you to see. So identifying metal ions. So every transition metal ion will be a different color with different ligands, but we can identify all the hexa-aqua ions, the ones with 6 water ligands, and we could also know the colors of some other specific ones. So the ones that you would need to know are below. So iron 2 is a pale green kind of color. Fe3 is a violet color. Vanadium 2 is purple. Vanadium 3 is a stronger green. I say just green. Copper 2, blue. Copper chloride, also copper tetrachloride, or copper tetrachloride 2 minus as an ion is, I remember it's a 2 minus because each chloride ion, copper in itself, it's a Cu2 plus ion, but each chloride is having a -1 charge. So it's knocking down it from Cu2 plus from a 2 plus to a -2, because you're adding -4 essentially in terms of charge. We're going from +2 and we're minusing 4. So going from +2 to -2. But copper tetrachloride 2 minus is a yellow color. Copper 2 hexa aqua, so cobalt 2 hexa aqua is a pink color. And cobalt 2 hexaamine is a straw yellow. Call it a straw yellow color, right? So there's some things here that so above as I've shown you, I've gave you the colors of certain ions, and while these colors are true, you might not always observe them in the color that you just expect them to see them as. So iron 3 in solution usually appears as yellow orange if it's concentrated, and that's because hexaaqua iron is quite acidic and will lose protons to become Fe H2O5 OH-, and this is a yellow color. So if you ask what the color of a hexaaqua iron 3 is, you should say purple, but just be aware that if it's in solution, you have more of a yellow solution. So out of solution, hexaaqua iron 3, Fe3 is a violet. Did I say violet? It's more of a purple color. I apologize. Sorry. This is purple. If I'm wrong, again, double check this for specification, because even I make the mistake here. Right? Yeah, but the point being, right, the Fe3 as itself would be more of a purple color, but once it's in solution, it appears as more yellow orangey, because, and I'll show you a little bit in a small scale what's actually going on here. It's actually going from iron 3 hexaaqua to FeH2O5 OH-, because it's losing a proton here. And I'll talk about the acidic properties in more detail in a later video, but I'll briefly explain it here, right? So this is the iron 3 hexaaqua, right? Now, I want to make it very clear, this has a very big impact on the biggest thing here is about the charge. The charge is all that makes a difference, right? So higher charged transition metal ions are more likely to be acidic in solution in comparison to, well, less positively charged transition metal ions. And there's a reason for this. So what's going on here is that the ligand here is ligands donate a lone pair of electrons to the Fe3+. Because this Fe3+ here is so positive, I'm going to use this example here, this ligand here, right? Because it's so positive, what it's doing is that it is pulling electron density on the oxygen atom of this water ligand even closer. So this would be more like here anyway. I think it'd be more like here. Yeah, because it's donating a lone pair of electrons to form a coordinate bond. So it's more, it's both the electrons are coming from the oxygen, right? But because this is so positive, it's pulling it to here, like to almost, more like here-ish, right? And what that's doing is that now that's because you're pulling electron density away from the oxygen atom and towards the Fe3+. What's going on now is that you're depolarizing this OH bond here. It could be this one or this one. I'm just going to pick this one for this example here. So now what's happening here is that this is becoming more partially positive. And this, remember, the hydrogen is already partially positive anyway. But because now this is more partially positive than partially negative, originally, if it was just like as it was before, right? Originally, it would be like this, where if this was just Fe2 plus,